Okay, sorry about that. A bit of technical issue. Let's continue with our problem. Okay, so we talked about this example yesterday where this guy started at the top where he was not moving, but he was at some height, right? He was at 10 meter from the ground ataupun 10 meter vertical displacement from our reference point. In this case, our reference point is the ground. Okay. So when this guy is at the top or at some height, we can say that this guy has potential energy, and that potential energy that he has is equal to, it's already there, which is PE initial equals to mgy initial ataupun mgh. In this case, they used y. Sama je, it's vertical displacement. It can be either y or it can be either h. PE is potential energy and the subscript I is for initial. You should know this by now. So when he starts diving, that part of his energy is converted into kinetic, and while the rest is maintained as potential energy. So he will dive and maybe he will reach this point of 5 meter from the ground. Now instead of mg times 10, now his energy is mg times 5. Now, where did the rest of the energy go? It became kinetic energy. So now you have KE at this point because this guy is moving. Your UG decreased and the energy that was lost from potential energy became KE. So KE, kita akan assume that KE will also have mg5 because mg5 times mg5 will give us mg10. Kat sini mg10. Bila turun, jadi mg5 plus Ke, and we are going to assume that we are not losing energy due to air resistance. So mg5 ataupun half of the potential energy that we had earlier has become kinetic energy. So I can say 1 over 2 mv squared is equal to whatever that was lost when he dived down. And then when he reaches this part, his h becomes 0. So now mg is mg0. So now our ug totally lost its energy, and we are going to assume that all of this energy has been converted into kinetic energy. So the entire ei that we had early on, which was mg times 10, is now E final, which is 1 over 2 mv squared. Since EI has to be equal to EF, this guy is kita boleh equate them together lah. And this is what we did yesterday. Yesterday, I think my steps was more organized, but this is just like the concept. I'm trying to discuss the concept here with you guys. This is the calculation part. This is what is going on here. Part of the energy is converted, and when he reaches the bottom, when you lose all of your potential energy, it has to go somewhere. Where does it go? It goes to kinetic energy. So that is what happened yesterday. So now we have another example 5.8. This is on an incline ataupun on a slope. So a skier starts from rest. So he starts from rest where U is equal to 0. U not potential energy, U velocity. Starts from rest at the top of a frictionless incline. So our job is easy. We know that if we are going to talk about conservation of energy, we know that it is just going to be EI equals to EF. The W and C is not here because it is frictionless. So it's great news to us. So it is on an incline of height 20 meter. So this is the vertical displacement as in figure 520. This figure lah. At the bottom of the incline, the skier encounters a horizontal surface. So mula-mula dia kat sini, from at point A, he goes down, reaches point B, and then he encounters a horizontal surface, okay, from B to C, where the coefficient of kinetic friction between the skis and snow is 0.2. This part is frictionless. No friction, but at this part you have that friction. Find the skier's speed at the bottom. Here it's asking us to find out what is V at point B. This is the question. And then how far does the skier travel on the horizontal surface before coming to a rest? Now, after you found out what is V at point B, they are asking you to find out what is S when U is this guy. Let's say this is VB. When U is VB and V is 0 before it comes to a rest, right? So neglect air resistance. We don't have air resistance here. We don't have friction here, but we have friction from B to C. So we can ignore this part first. Let's not confuse ourselves. Let's solve this to find out what is the velocity at B. So this is the strategy. Strategy dah bagi dalam textbook ni. Going down the frictionless incline is physically no different than going down the slide of a previous example and is handled in the same way using conservation of mechanical energy to find the speed V at the bottom. On a flat rough surface, use work energy. Okay, kita abaikan dulu yang tu. Kita start with A to B dulu. Alright, so let's do this. So we start with EI equals to EF. Can anyone tell me what should be in my equation for EI? Semalam saya cerita je, hari ni kita kena discuss. So what should be in my equation, guys?
Kinetic and gravitational.
Gravitational potential energy, okay. What is that? What's the equation?
UGH.
MGH. Correct. So if I were to write dia punya term sahaja, I would say UG plus KE. This is I and this is I. And this is UG final plus KE final. Thank you for telling me that. So UG tadi ada orang dah jawab dah. Thank you. MGHI. And what about KE? What is our KEI? What is our velocity initially?
Zero.
KE is 0. So this is going to be easy for us. What about our UGF? We are assuming that point B is our final for part A.
Zero.
Because this is our reference height. Okay, dia tak bagi, but kita akan assume when we reach the ground, yang tak ada incline, we are going to assume that is our 0, H equals to 0. So this guy becomes 0, and we are left with 1/2 mvb squared. VB referred to this guy, the velocity at point B. So it seems pretty easy lah at this point. So M is, we don't know, dia tak bagi kan, M tak bagi, 9.81. HI, what is my HI? Is it this length over here, X, or is it H over here?
H.
When we're talking about MGH, it's always the vertical displacement. Vertical displacement as in Y. So this is going to be 20 and this is 0. And this is going to be equal to mvb squared. Since we have m on both sides, kita boleh abaikan ni kosong. So we can just cut it out. So we don't have to solve for m. So just using our calculator, 9.81 times 20 times 2, and then square root that, I would get VB as 19.81 meter per second velocity. So we got our velocity at B. How do I solve part B? How far does the skier travel on a horizontal surface before coming to a rest? How do I solve this one? Anyone? So we have U. Yes, nak try ke tadi? We have V, which is 0, because the ending point is going to have a 0 velocity because it's coming to a rest.
V squared equal to U squared plus A tak ada.
Tak ada, okay. So macam mana tu? Okay, let's see the strategy. On a flat rough surface, use the work energy theorem. Equation 5.13 with NC. Oh, we forgot, we have friction, right? So we have EI minus WNC, non-conservative work done, equals to EF. This is our equation. And we also have work energy theorem whereby the net work done is equal to KE final minus KE initial. So we have our initial value, we have our final, this is a 0. Sorry, our final is a 0. So what else? What other information do we have? To the friction times T. Come on guys. Okay, jom kita tengok jawapan. So kita dapat jawapan sama untuk yang VB kita. And then how did the textbook does it? So dia cakap W net equals to minus FKD, which is, this is the work done to overcome the friction, and this is the change in KE. Why is that? Does that make sense? Kenapa dia equate W net as change in KE? Is this correct or not? Ta-ta-ta.
Because ada change in velocity ke?
Because apa tadi tak dengar?
Ada change in velocity.
Because we have a change in velocity, correct? And there is no other UG tak ada involved, our US pun tak ada involved, we're just focusing on velocity change. So that was the condition to use work energy theorem, right? So there is a change in velocity and only change in velocity, therefore we can use the work energy theorem. However, kenapa dia equate to WNC? Kenapa? Where did this equation come from? Okay, I'm going to give you a hint. So I had EI minus WNC equals to EF. What is my EI for that situation? From B to C, what is my EI and what is my EF? How do I expand my EI and EF? What should be in my EI? Ada UG tak?
Ada.
We only have KE, right? UG tak ada because we're not changing in height. So UG is just a 0, UG initial and UG final is both 0. Tak ada UG is not involved. So we have KEI here, we have WNC, and we have E final is only KE final. So this looks familiar. So now we have KE final minus KE initial, and this is equal to WNC. Does that look familiar? It's the same. Or this is also the work energy theorem. W net equals to change in KE. This is the work energy theorem. However, kat sini kita punya W net is only this guy. Okay. So when we have friction, we are doing work to overcome the friction, and this is equal to the change in kinetic energy. It will become slower. The velocity will become slower, or in this case, dia dah bagi tahu kita siap-siap, our velocity will come to a rest. The V will become 0, and we know that that would give us a negative work done, which is the work done to overcome friction. So if this confuses you, just go for this lah. Or you can just go for this. You would get the same answer. Whichever approach, you would get the same answer. Now, if I use this one, the one that we're comfortable with, this equation. I'm assuming everyone is comfortable with this equation. Ke tak ada yang comfortable pun? Semua tak comfortable sebab semua tengah susah belajar. Okay, hopefully kita akan comfortable lah with this equation. So EI is KE initial, and this is my WNC. Sorry, this is WNC. Tersilap tulis. And this is KE final. And we know that our KE final should be 0 because velocity akan jadi kosong. And KE initial is going to be 1/2 mu squared. U as in value yang kita dapat tadi. Okay. The U is 19.81 and our V is 0. 19.81 and and then our V is 0. So this becomes 0 and this becomes WNC. WNC is force of friction times with displacement equals to 0. So do I know what my friction is? Can I find it? Let's see. So I want to know what is my friction. This guy is over here. Wow. Let's assume he's a box because I can't draw. So he's a box. So I have R. He's moving this way. I have F, which is horizontal. And F is equal to mu R. What is my R here? What is my R here?
R equal to mg.
R is mg. We're not on an incline. Kalau incline ada mg cosine theta lah, ada mg sin theta lah. But now we are on a horizontal surface and the box ataupun the skier is not flying. Therefore, our net in the Fy is equal to 0. So what is in our y-axis? It is R minus mg. So my R is basically just mg. So senang sebenarnya. So back to our equation here, my friction is just mg. So mg, I know what my u is. Let me kecilkan benda Allah ni kejap sebab tak cukup tempat. Or I should write it on the other side kejap. Oops, kejap Kejap. What is it? Yes, mommy is teaching. Can you go outside?
I want this one.
But you are noisy.
I want that.
Okay, don't be noisy. Alright. What?
This one.
No. Okay, bye-bye. Bye-bye, mommy teaching.
I mean, idea.
No idea. Lepas tu, we have our U. So M, we have U tadi berapa tadi? 19.8, right? 19.8 squared. Was it 19.8? 19.81. Okay, and then F is mg. And then D we don't know. And then this is equal to 0. So if I bring this mgd to the other side. Come on, let's go. Come on.
I want color.
Yeah, later.
I want color.
Go, mommy teaching.
I want color.
No. Okay, sorry about that. Ada gangguan. Okay, so back to our equation here. So mgd, we bring this to the other side, it becomes a positive. So 1/2 m 19.81 squared. So m cancels out. I can solve this and I can know what is my d. So let's see if we get the same answer as the textbook. We divide it by 2. 19.81 squared divided by 2 divided by 9.81. I would get my distance as 20 meter. Okay, so let's see. Betul ke? Lain. Kenapa lain?
Tertinggal mu.
Okay. F is mu. Mana tadi? Okay, sini. Saya tertinggal. So F is mu mg. Mu is berapa tadi? 0.2. Okay, mu is 0.2. Mg is mg lah. 9.81. So this is my F. Tertinggal tadi. So this becomes 0.2 mgd. 0.2 mgd. Thank you. Saya pun terlupa. 0.2 mgd. Okay. So hopefully sekarang betul. Let's see, 19.81 squared divided by 2 divided by 0.2 m potong divided by 9.81 dapat 100. Apa yang berbeza kat sini? Saya dapat 100 instead of 95.2. So kat sini dia pakai 0.21. Oh, saya pakai 0.2 je. Okay, ada perbezaan kat situ lah. And then my G I use 9.81. Dia pakai 9.8. And then this 19.8 I use 19.81. So ada decimal places yang berbeza kat sini. So that's fine. So we get our 100 meter or 95.2 if you use the values as the textbook. Okay, so does everyone understand what happened here? First, what we did was, first we had UG over here, KE was 0. And then when we reached B, we know that UG was completely transformed into KE. So this is what happened earlier on, and we did that equation. EI equals to EF, UG plus KE, UG plus KE, where KE initial is 0, and then the final side UG became a 0. So UG completely transformed into KE, and we found out what was velocity at point B. And then this velocity at point B now becomes our initial velocity, and we have friction going on. So we use this equation EI minus WNC because we have friction. So there is work done to overcome non-conservative forces, and this is equal to EF. However, since we are on this horizontal surface, there is no H involved, there is no elastic potential spring involved. So we know that there is only a change in velocity. So we can use the work energy theorem. In this case, it is KE initial minus WNC KE final. So nanti bila kita rearrange, this looks exactly like the work energy theorem. Looks exactly the same. And we know that from the work energy theorem, if our velocity is decreasing, our work done will be negative. So indeed, our velocity was decreasing from 19.81 to 0. So negative W. So and then we use that, kita substitute all the values. Okay, we just substitute macam biasa je. Kita cari friction pakai free body diagram. And then you got your answer as D. Any confusion for this example? Is everyone okay with this example?
Okay.
Yeah.
Okay.
Okay.
Okay, thank you guys. Let's move on to our spring example now. Okay. So this is example 5.9 in your book. If I'm not mistaken, it is in page 139. Page 139 dalam e-book. Kalau ada orang tak pernah buka buku lagi, this is the time. So problem, a block with mass of 5 kilograms. So this guy is 5 kilogram. Is attached to a horizontal spring. This is the horizontal spring. Kejap, let me rearrange this sikit bagi besar. Ya Allah, kejap ini. Okay. Attached to a spring, to a horizontal spring with spring constant of 4 times 10 to the 2 Newton per meter, as in figure 5.22. The surface the block rests upon is frictionless. Yay. So kita punya EI will be equal to EF. Frictionless, eh? If the block is pulled out to XI of 0.05, they're pulled out. So this is our equilibrium position marked as 0. X equals to 0. So it is being stretched out, and then dia akan reach XI at 0.05. And then it is released. Find the speed of the block when it reaches the equilibrium point. So kita tackle yang first dulu. Find the speed. Kita nak tahu lepas kita tarik dia, kita lepas, kita nak tahu, hey, what is the V over here as it swings back. Bila kita tarik spring kan, kita lepas, dia akan swing back to its original ataupun kadang-kadang dia akan terpergi jauh sebab banyak energy. So we want to know what is the V when X is back at 0. Okay, so our initial will be here and this is going to be our final position for part A. So let's do that. So our E initial is equal to E final. We don't have non-conservative work done because this is frictionless surface. So what should be in my EI here? What should be in my EI equation?
UG,
Hmm?
US,
US. What is US? So UG is MGH, US is
1/2 KX,
1/2 KX squared. Jangan lupa squared. So this is going to be I, and then we have US final plus KE final. So this is our equation that we're working on. So tadi kita cakap pasal UG, now we're just talking about US. So US is 1/2 KX squared. Selalu orang tertinggal squared ni. Selalu memang selalu sangat sebab dia confused dengan F equals to KX. So don't make that mistake. 1/2 KX squared. And then we have our 1/2 MV initial squared. This is going to be equal to, this is initial. And this is going to be 1/2 KX final squared plus with 1/2 MV final squared. This final state is going to be at this point. This is very important to take note. Okay, so now, apa yang kosong dalam equation ni? Apa yang kosong? What is going to be 0 in this equation?
KE initial,
KE initial is going to be 0, betul. Sebab bila kita tarik tu, it's not moving yet. Kita baru tarik so kita baru provide that energy and that energy is in the form of 1/2 KX squared. Sama macam diver tu baru nak start tapi dia tak bergerak lagi kan, dia baru nak start. So his initial state was only MGH and tak ada KE lagi. So KE dia kosong. Sama kat spring juga, baru nak start tapi tak ada KE lagi. So kita hanya ada 1/2 KX squared here. So our 1/2 K is 4 and X is 0.05 squared. And this is equal to, what is the value for our 1/2 KX squared here? What is our X final?
0,
0, because this is where we said we wanted to find the V, right? So that is going to be our final place. So now this guy becomes 0 as well. This was plus 0. And then we have our 1/2 M. M is 5. And V final is what we're trying to look. So now we can solve for V final. Yep.
K tu patut 400 kan? Sebab 4 times 10 power of
Oh
2.
yes, betul. Thank you. 100%. 400. Ada lagi tak saya tersilap? 0.05. Okay. Thank you. Saya tengok sekali macam tu je. Okay, so 400 times 0.05 divided by 2. Sorry, 0.05 squared divided by 2. So I get times 2 divided by 5, square root that. I'll get 0.44. Is that the answer? 0.447, yeah, sama. So V final is 0.447 meter per second ataupun 0.45, boleh. 2 decimal places. Tapi untuk web assign, diorang suka 3 significant figures. 3 significant figures, betul lah. So they want that 3 significant figures tu web assign punya style lah. Tapi untuk exam, just 2 decimal places is enough. Okay, what else? Okay, B. This is part A. Part B. Let's use a different color because I get confused. Okay, part B. So part B, find the speed when x is 0.025. Tadi kita punya V, kita cari dekat kosong. 0.025 is midway. Xi tadi berapa? 0.05. Now it's asking us x final equals to 0.025, which is halfway. 0.025. Okay, can anyone predict, will our velocity be higher or smaller? Velocity smaller ke bigger? Sorry, smaller ke bigger? Velocity at 0.025. Macam mana? Agak-agak aje.
Smaller. Smaller.
So bila kita tarik, dia patah balik. So dia patah balik tu, dia punya speed kat sini smaller. Bila dia sampai dekat equilibrium point, dia jadi lagi laju. Okay, so let's see if that is correct. So our V final is now 0.025 dekat point sini. Sorry. So EI equals to EF, sama je step dia. USI, KEI, USF, KEF. And then what else? This is 1 over 2 KXI squared, 0 equals to US K final squared. And then this is 7.4. So, let me make this smaller because we're done with this guy. Do not take the B. Kenapa dia cakap dah group? What is this? Sekejap Hari ni please behave. Okay, boleh. Let me make this smaller. And we have space. Okay, we will see if our velocity decreases ataupun dia lagi kecil ke ataupun lagi besar. So let's see. This is 1 over 2 kxi squared plus 0 because we started with 0 velocity equals to 1 over 2 kx final squared and 1 over 2 mv final squared. Now this guy does not become 0 because our x final is not a 0. It is 0.025. So our initial energy is divided between two components ataupun two types of energy, which is the spring potential energy and also the kinetic energy. So I'm going to assume that kinetic energy akan lagi rendah daripada this guy lah. The kinetic energy is going to be smaller and therefore the velocity is also going to be smaller. Sebab dia berkongsi tenaga antara US dengan KE. So let's try to solve this. This is the easy part, just putting in the values, 0.05 squared, and then this is going to be 400, and this is 0.025 squared, plus 1 over 2. M is 5, and V final is what we're trying to find. Okay, so hopefully, because I'm lazy to use a calculator, let's see. 1 over 2, This is part A. Where's part B? Where's part B? Okay, it's this one. So find the speed half. Dia buat cara lain pula daripada kita. Alas, betul. So dia dapat jawapan 0.387. Okay, let's see if we get the same answer. I don't like the way they structure the equation. Selalu confusing. So let's see. 1 over 2 times with, macam nak kira. Dah lah petang. Squared divided by 2. And then this is 0.5. Can someone calculate this for me as well to double check? 0.25 divided by 2. This guy is 0.125 for this guy. And then we have 0.5 minus 0.125 times 2 divided by 5 square root. So I get my V final as 0.387 meter per second. Okay, sama So kita tak ada shortcut untuk this style this type of problem, we don't have shortcut. So if you're wondering, oh kan dia halfway daripada yang tadi kan, kenapa tak bahagi 2 je? Tak boleh sebab dia ada square kat sini. So this square will mess us up if we don't be careful. Kadang-kadang diorang tengok, oh separuh perjalanan je, maybe this velocity is half. No, it doesn't work like that. You have to use the equation because ada square tu dia jadi complicated sikit. So don't use a shortcut. Use the EI equals to EF. Put in the values betul-betul. Okay, tak boleh bahagi 2 je terus. Alright, so next one. What is C? C is repeat part A. If friction acts on the block with coefficient mu K, coefficient of kinetic friction 0.15. So dia suruh ulang A, maksudnya kita punya X final adalah X equal to 0 tapi ada friction. So now let's do that. Let's duplicate this and see what's the difference. This is part C. Okay, so let's do C. So C dia cakap EI minus WNC equals to EF. Tadi EI equals to EF je. Now we have the WNC because we have friction. So EI kita patut samalah. Kita started with the same condition. 0.05 squared, and then this is going to be friction times distance. This is going to be equal to EF. EF is this is our X final. So at this point our US ataupun our 1/2 kx final squared is going to be 0. And then 1/2 m is 5, and then final V final. So I'm predicting a smaller velocity. Sebab apa? I'm predicting a smaller velocity than this V final because we have to overcome friction. So our energy is lost due to friction. Remember, friction, kalau energy lost by friction, kita tak boleh recover. It does not get transformed. It is lost into the environment. So that sucks, but this is what it is. So 1/2 mv squared. Now we need to find out what is F and what is D. Can anyone help me? What is F and what is D in this case? What is F? Jangan tengok textbook.
Mu mg.
Mu mg. Kenapa
R.
Because the R is kalau tengok sini dia kasih free body diagram dah, dia senangkan hidup kita. So the box is not flying, net in the Fy is equal to 0, therefore R is equal to mg. Betul lah tu. F equals to mu mg, and our D. What about our D? What is our D here? What should be the D?
0.05.
0.05. Saya dengar tadi ada orang jawab 0.05. Yes, correct. It is 0.05. But is it a positive or a negative 0.05?
Negative.
Because kita stretch, at this point kita tak gerak lagi. Bila kita lepaskan, the displacement is towards the left. Boleh bayangkan spring tu kita tarik, lepaskan, it's moving to the left. So the D in this case is minus 0.05. Remember I told you untuk spring, kita memang kena define the positive and negative betul-betul. Sebab direction dia tu ada makna lah, and it will help us. Okay, so this is our FD. Kat sini kita dah letak negatif siap-siap dah. So that negative is this lah, okay, coming from the D over here. Okay, so kita akan letak. So minus mu mg times 0.05 equals. Okay, so kadang-kadang ada orang confused. Okay, doktor, kalau WNC equals to FD, then this is minus whatever this is, mu mg 0.05. Betul kat sini minus WNC. So dia letak minus. Tak boleh minus mg 0.05. Tak, it doesn't work like that. So kalau you put your WNC kat sini mesti kena negatif juga sebab dia nak kena lose that energy. If you put a positive value, you are increasing the energy on the initial side. This is not how it works. Friction sepatutnya mengurangkan energy. So if you get this negative, letak je lah negatif tu. Tak payah fikir dah negatif WNC, oh kena darat lagi sekali negatif. Tak. Letak je negatif kat situ. It has to lose energy. Remember that point. It has to lose energy. You're doing work and you're losing energy to friction. So kena negatif. Tak kisah dapat apa kat sini, negatif kat sini. Okay, I hope I'm clear on that. Kena lose energy eh. The aim is to kurangkan energy kat situ. So minus mu mg 0.05. Faham ke semua apa yang saya cerita tadi tu? Faham Okay. So now kita tahu dah EI kita memang kena kurang energy daripada yang part A ni. Sebab kita kena do work to overcome friction. So malas nak kira. What is mu? Mu is 0.15, M is 5, G is 9.81, 0.05. Saya kena kira juga sebab saya tahu jawapan equation diorang akan buat macam lain. So it will be confusing. Fine, saya kira. Dapat
0.367 0.37
ke 0.37 berapa?
0.37.
Okay, 0.37. Let's see. Thank you. Ada orang tolong rajin kan? Tempat lain. Okay, we need to figure.
Saya dapat 0.230.
Okay, so tersilap kira kot tadi 0.23 Sebab sama dengan ni. So pakai equation saya kan? 0.23 tu kan?
Betul tak?
Okay. 0.23 Okay, so does everyone understand what was happening here? And cara nak solve spring yang horizontal? Okay, kejap. Kejap. Coming. Is Daddy here? Daddy here? Daddy here? Oh. Okay. So, okay, previously for the first part we don't have friction kan, so we had EI equals to EF. Untuk spring system, we don't have mgh. We only have spring potential energy and also kinetic energy. So when we stretch it, the kinetic energy starts with 0. When we let go of it, the the US is converted into KE and also US as it goes along the displacement lah. So if it goes back to this part, the US is completely transformed into KE. Kalau dia patah balik ke original position dia. Sebab tak ada displacement, therefore potential energy akan jadi kosong. Potential energy punya equation 1/2 kx squared. Kalau x kosong, kosong lah 1/2 kx squared tu. So all of the energy that we gave that spring is now converted completely into KE. So at this point, KE is the maximum lah. We would say that the KE is the maximum because all of that energy is converted into KE. If it reaches halfway point kat sini, part of the initial energy is converted into KE sikit and separuh lagi retained as, bukan separuh lah, some of it is retained as 1/2 kx squared. Okay, and then when we had friction, this is what happened. Is this with friction? No, this is with friction. So EI minus WNC. Macam mana nak tahu friction? Tengok free body diagram. Cari pakai free body diagram. What is your reaction force? Okay, so I think this is quite straightforward as long as you understand what's going on. Should be okay. Ada tak yang part yang confused kat sini? Yang saya nak kena repeat? Please let me know. Ada tak yang confused? What is this? Oh, this is velocity. So everyone is okay? So everyone's okay? Okay. Let's move on to the next example. This is soalan sama ke lain? Sama. So ni jawapan dia dapat sama. Okay, so circus acrobat. So a 50 kilogram circus acrobat, betul kan? Drops from a height. So dia tak tahulah datang dari mana, tapi dia drops at a height. Dia start dari sini kaki dia. Drops from a height of 2 meters straight down onto a springboard with a force constant of, so spring ni ada spring constant K equals to 8,000 Newton per meter. So dia drop from a height of 2 meter. By what maximum distance does she compress the spring? So dia daripada atas ni, dia terjun by 2 meter yang kita tahu. Tapi this is when x is equal to 0. So bila dia duduk atas spring tu, dia akan compress juga spring tu. So dia sebenarnya turun by h plus d. D tu adalah compression of the spring. So the compression of the spring is equal to minus D. Kita akan go down, compression minus D. It is not positive. Kalau positive kita stretch. Kalau kita compress, it is minus. So this is X of the spring. But the height of this curl, of the acrobat, the height of this acrobat ataupun the vertical displacement of this acrobat is H plus D going down. Going down Dia ke bawah, bukan ke atas. Okay, so this is what we know. So dia start dari sini, dia jatuh, compress, spring. Itu je yang kita kena tahu sekarang ni. Okay, so by what maximum distance does she compress the spring? So this is the strategy. Non-conservative forces are absent. Tak ada air resistance here. So conservation of mechanical energy can be applied at the 2 points of interest, the acrobat's initial position and point of maximum spring compression. Her velocity is 0. So dia cakap kat sini, bila dia sampai dekat hujung ni, when dia stop, bila dia compress spring tu, dia stop kan? Dia tak bergerak dah because tu compression. Bila awak duduk atas spring pun tak bergerak kan? So V is final. V final dia adalah kosong. Susah juga problem ni sebab ada dua jenis. Dia punya displacement tu ada H dengan D So let's try it. So V final adalah kosong. Kat sini pun kosong juga. So let's see. At the 2 points of interest, the acrobat's initial position and the point of maximum spring compression, her velocity is 0. So dekat initial and point of maximum compression. At this point, the V is initial is equal to 0. At this point, the V final is also equal to 0. This is what the strategy is telling us. So the kinetic energy terms will be 0. The kinetic energy terms will be 0. Choose y equals to 0 as the point of maximum compression. So the strategy here is to label this as y equals to 0 and this as y equals to h plus d. Kan? Okay, y equals to 0 bila kat maximum compression. Y equals to h plus d at the top yang dia nak terjun tu. Okay. So that the gravitational potential energy is 0. This choice also means that the initial position of the acrobat is h plus d, where the h is the acrobat's initial height above the platform and d is the maximum compression. Okay, so penatnya baca soalan ni. Panjang gila. Okay, so we know that this is y equals to h plus d and this is y equals to 0. This is the strategy. Strategi ni tak wujud dalam exam. Ni strategi exam textbook kita. Kita belajar bersama textbook. So this is the strategy they are recommending us to follow. So this is V initial 0. Bila saya baru nak mula terjun, saya punya kinetic energy tak ada lagi. V equals to 0. Bila saya sampai kat bawah ni pun, I'm also static. So the V is equal to 0. So if I write my equation EI equals to EF, what terms would I have here? EI equals to EF. I would have mg. This acrobat is going down, right? So dia ada mghi, and at this point kita boleh cakap ada 1/2 kxi squared. We don't know if there is or not. Nanti kita akan discover. And then we have our mgh final. Let's label this as y lah, because kita ada h kat sini, so akan jadi confusing. So let's label this as our y initial, and this is our y final. And then 1/2 kx final squared. Let's see. So there is no work done. There is no non-conservative work done. Non-conservative force. There is no work done for non-conservative forces. So this is just our equation. So let's try to plug it in. M is 50. G is 9.81. Yi is our initial is H plus D. H is 2. D tak tahu. 2 plus D. Boleh tulis macam tu. And then 1/2. And then we have 8,000 as our K. And then our X initial kat sini tak wujud lagi kita punya spring. We haven't started anything yet. So this is non-existent sebenarnya. Kita kat point sini, kita punya spring tak buat apa-apa lagi. Spring kita, hello, tak buat apa-apa pun. Saya duduk di sini saja. So 0 lah. It has not started. The spring has not started doing anything. So we are going to assume it is in equilibrium. Therefore, the X is just 0. Walaupun this acrobat is in the air, the spring is not affected. The spring is like, yeah, go on. Terjun je lah. Tak adalah, dia tak affected pun lah at that point. Tapi bila dia dah terjun, kena dekat spring tu, baru dia affected. So baru kita fikirlah nak jadi apa kat dia. So that is M50. G is 9.81 and the Y final, kita tahu, kita define this final point as 0. Okay, this was the strategy. And plus 1/2, 8,000. And the X final is minus D. Bukan H plus D, it's just D. Sebab spring ni punya displacement hanyalah minus D. Okay, oops. Oh sorry, kalau energy kita tak letak lagi kot. Kejap, let me think. Kena ada positif ke tak ni? Kena negatif ke tak? Kejap Oh, this is squared, so it doesn't really matter. Okay. So, alright.
Betul.
Yep.
KE kita kosong sebab B dia kosong. Macam tu. Sebab tu kita letak KE.
So this is our initial place. This is our final. Bila dia baru mula nak terjun, velocity kosong kan, macam diver kita tengok tadi. Diver tadi. Diver ni kan, mula-mula KE kita kosong. Sama juga macam acrobat ni juga. Mula-mula KE kita kosong. Tapi diver ni bila dia cecah air tu final point kita kan. And bila dia cecah air tu, dia masih bergerak sebab dia masuk dalam air kan lepas tu kan. So dia masih bergerak. KE dia tak boleh kosong. Tapi kat sini, bila dia dah compress spring, dia dah tak bergerak lah sebab dia tak adalah pergi mana-mana dah. Dia kat situ je kan. So KE dia dah jadi kosong. Okay.
Okay, thank you Dr.
Okay. So kat sini conversion between UG and US sahaja. The KE is equal to 0. I admit this is not very intuitive. So biasanya kita akan assume akan ada velocity final kan. So for this type of problem, velocity dia bila dia dah tak bergerak, kita akan cakap KE dia kosong lah. Okay, so kena ingatlah juga sikit sebab dia tak intuitif sangat kan. So perbezaan the acrobat and the diver is that this is our final position. Ni air kan. Diver tu dia bila dia terjun, dia tak adalah kepala dia okay stop kat situ. Tak kan, dia gerak lagi kan. Dia terus bergerak masuk dalam air. So there is a difference lah between the diver and also the acrobat. Bila acrobat ni sampai sini, dia stop. Diver ni kalau nak stop, kepala dia cecah air. Macam mana dia nak stop? Tergantung lah macam I wouldn't say that word lah, but weird lah, okay. So that is not what happens. So KE diver ada value final, tapi acrobat tak ada. Okay, so now we try to solve it. Hopefully we get it. We are trying to solve for D. Okay, so 50 times 9.81 times with 2 dapat 981. Tak cukup tempat lah. Oh, I have a chat here. Saya tak perasan. Can we change the reference point to solve for P? Oh, this was early. Sorry. Sorry, Rais, tak perasan awak punya soalan. Okay, kita macam mana saya nak buat ni? Tak cukup tempat. Oh, I know, because I made this big. Kita akan kecilkan dia. Group way. I should have just duplicated. Group. Kecilkan. Mana VI dia? VI kat sini. So, besarkan sampai sini. Okay. This one. Kat mana tadi? Oh, kat sini. Okay, so let's continue with our calculation. Malas ni. 981. Okay, I shouldn't say malas lah sebab I'm the teacher here. So 9.81 times D. 490.5 490.5 D equals to 50. This is kosong. Yay. And then we have 8,000 divided by 2. And we have 4,000 D squared. So this is a quadratic equation. What do we do with the quadratic equation? I'm not going to solve it using my head. So I'm going to use a calculator. So tekan mode 3 kali, go for equation, tekan kanan, tekan 2 degree. Okay, and then your A is 4,000. Kalau nak lagi senang, kita rearrange siap-siap. 4,000 D squared minus 490.5 D minus 981. So B is minus 490.5 and C is minus 981. So I would get D as Y. Kenapa asyik tak cukup tempat ni hari ni? So D is, it's not good place to write it. So D is 0.56. And there is another value of D equals to 0.43. Which one should I use? Which one should I get?
Positive.
Take the positive. So let's see. Betul, 0.56. Always take the positive value lah. Okay. Okay, so the other solution 0.437. Okay, dia ada kasih remark kat sini. This is what I like the textbook. Dia explain kenapa kita ambil positif, kenapa kita ambil negatif. Can be rejected because D was chosen to be a positive number at the outset. Was it? A change in the acrobat's center of mass, say by crouching as she makes contact with the springboard, also affects the spring compression, but that effect was neglected. So I remember Rachel. Rachel is from this class, right? Rachel talked about the center of mass. Yes. So Rachel talked about the center of mass. If you haven't watched Rachel's video, go ahead. It's quite interesting. Sebab dia, the center of mass plays a role in how to what do you call it? Lontar, I don't know what it's called. So center of mass plays a role. So this is what it's saying here. When the acrobat crouches, dia buat macam ni center of mass dia akan berubah, and that affects how the energy is distributed, ataupun it has some effect lah on the overall system. We say that the acrobat is a system lah. So it will be different. So now we are assuming that the acrobat, bila dia lompat, dia tegak. Okay, which is weird. So, but this is our assumption to make our life easier. Okay, so kita tak ambil ni. Okay, going back to this, D equals to 0 minus 0.437 can be rejected because D was chosen to be a positive number. Okay, let's go back to what we talked about just now. So saya ada tersilap buat So tadi kan, saya assume This was going down negative. Tapi kat sini saya tak consistent. I put 2 plus D where the acrobat was going down. So D was patutnya negative lah kan. This value should have been negative if I wanted go down to be as negative. But I didn't. I said this is a positive but this is a negative. So tak tally lah kat sini. So sepatutnya dua-dua positif. So I'm assuming this entire thing going down is a positive. Boleh if I am consistent. If I want to make it all negative, boleh juga. So this becomes minus 2, minus T, minus T juga. But lagi senang ambil positif. Sebab kita memang ada satu direction je kan. Direction ke bawah sahaja, so we can take it as positive. That makes our life easier. So if you have atas bawah, then atas akan jadi positif, bawah jadi negatif. If you have only one direction that you're going to, use that direction as your positive. It will make your life easier. So that is a little bit confusing lah. Okay, I have to admit. All right, next one. Example 5.11. Okay, we already spent about 1 hour doing examples and we're not in a hurry sangat. So let's take a break. If you have any questions, you can ask me. So let's take a break for 7 minutes and come back at 3:17. Take your water, go to toilet, whatever it is, as long as you come back and not sleepy. Okay, 3:17. If you have any question, boleh tanya. Oh, sorry. Oh, I have one chat here. Doktor, persoalan yang horizontal spring tadi, apa maksud dia by reaches equilibrium point? Okay, nanti saya cerita balik Aida. So equilibrium tu saya baru cerita semalam. So I think that's a new, I think you guys are macam tak masuk kepala lagi kot. Sebab baru sangat cerita equilibrium. Nanti saya cerita balik Sekejap, lagi 4 minit saya cerita. Ngantuknya. Jangan mengantuk. Korang jangan mengantuk. Saya pun tak boleh ngantuk. Kita kena bersemangat. Alah nak hujan. Rai, are you there? Tadi saya tak jawab soalan awak. Can we change the reference point to solve for B?
Ada doktor.
Maksud awak apa?
Soalan yang ski slope tadi.
Aha. Awak nak change reference point macam mana? Maksudnya?
So maksudnya kan boleh guna yang H tu untuk cari jawapan, tapi equation dia tak guna point H. So tak payahlah tukar reference point tu. Yang untuk B tu kan.
P. Dia tak pakai. Betul. Dia tak pakai H pun. Sebab
Thank you doktor.
Okay. So tadi Aida nak tanya pasal equilibrium position. Kita akan cakap sikit lagi pasal tu. This one. Princess. Okay, it's time. Okay, thank you for your questions. Tadi Rai tanya, boleh ke nak tukar reference point? Tapi saya tak faham sangat Rai tanya apa. Tapi Rai cakap it's okay. And then Aida ada soalan pasal equilibrium. Equilibrium point. Okay, let's go over this problem again. Kita discuss what the question means. A block with mass blah, blah, attached to a horizontal spring. So this is our block. It is attached to a horizontal spring. With a spring constant as blah blah blah, the surface, the block rests upon is frictionless. Maksudnya kita tak ada WNC. If the block is pulled out to 0.05, dia stretch. Bila kita stretch, kita akan, okay, saya ulang balik. So this is our spring. Remember I told you guys yesterday kita ambil hujung spring ni as x equals to 0. This is also known as the equilibrium point ataupun equilibrium position. When the spring is stretched, it is stretched to x equals to some value. This value is x equals to 0.05 meter. So this is a positive value. So bila kita tarik, dia kat x 0.05. So this was our initial condition, KE kosong. Bila kita lepas, KE mula and our US starts to decrease. So when it goes Bila kita lepaskan, dia akan patah balik ke x equals to 0. So this is what the question says. Find the speed of the block when it first reaches the equilibrium point. Bila dia patah balik and kita nak tahu what is the V at this point. So this is our V final at x equals to 0. So this is what it means when it reaches the equilibrium point. This is the keyword. Keyword equilibrium point untuk spring system, x equals to 0. Alright. So Aida okay ke? Saya jawab soalan ke?
Okay, Doktor. Thank you.
Okay, welcome. Kalau soalan lagi pasal spring, tanya. If I'm not sure, I will get back to you guys. So just ask away. Okay, next. Kita dah buat yang ni. So here, we assume that when the acrobat started, the V was 0. And when it stopped, ataupun when she compressed the spring, the acrobat was not moving. So KE was also 0. So this is different than the diver. So kena try to make sense of the situation sebab nanti kena apply untuk example lain. I mean, apply untuk problems in the web assign later. Okay, so next one, this one. Okay, so ni we have a spring and we have a block. So kat sini dia label kosong kat sini. So remember I told you when x equals to 0, that is the original state of the spring. If it is not at 0, maksudnya it is either being stretched or being compressed. So let's see. A 0.5 kilogram block rests on a horizontal frictionless surface in figure 5.24. The block is pressed back against a spring. So press against a spring having a constant of K equals to 6 to 5. So our K is 6 to 5 and we are compressing here. Kenapa kita tahu dia compress? Sebab dia cakap the block is pressed. Press maksudnya tekan kan? Tekan against a spring. Kita tekan kotak tu against a spring. So we are doing compression ataupun we are compressing the spring by 10 centimeter to point A. So point A is this guy lah. Okay, so this is 10 centimeter. Let me label this nicely. So this is equal to 10 centimeter. Why is it so small? Okay, then the block is released. Kita tekan, lepas. So bila kita lepas, that potential energy will be converted into kinetic energy and part of it will be retained depending on where it is lah. Then the block is released. Find the maximum distance D. The block travels up the frictionless incline if theta is 30 degrees. So it's asking us how far, bila pas dia release tu, how far will it go up the incline? So what do we know from the examples that we have done so far? Kita kena cari V at this point ataupun we have to know what is our U V initial lah. We have to know what is our V initial at this point. And then naik block ni kita akan fikir kemudian lah. So we just need to know, hey, what is the VI over here? Okay. So let's figure that out. Okay. So we compress 10. Okay, how fast is the block going at half its maximum height? Oh, ada lagi. Lepas tu dia tanya, apa speed dekat sini? What is the V over here? Oh, dia tanya D, dia tanya V kat sini. Banyak kerja. Okay, so strategy. In the absence of other forces, conservation of mechanical energy applies to part A and part B. So we are assuming both incline and also the horizontal surface is frictionless. So in part A, the block starts at rest. Kita tahu bila kita start spring je, kita start dengan US. KE tak ada. Okay, so that is our approach lah so far kan. Okay, let me go back. Let me go back to what we have done so far. Kita start yang spring tadi. Okay, spring ni kan. Kita assume kita punya KE was always 0 starting for a spring. KE is 0 for the starting of a spring. Sama juga kat sini. Starting for a spring, KE dia 0. So EI equals to EF. Our KE is 0. But let me just write down the basic equation dulu. This I and this is U final, US final. US final plus KE final. Okay, so U as KE initial is 0 and that is what I know so far. So 1 over 2 kx squared. We started at this over here, 10 centimeter. Kx squared initial plus 0 equals to, we want to know what is the V over here. So what is it going to be? Oh, kita tak tengok strategi lagi kan? Lupa. Part A, the block starts at rest and is also instantaneously at rest at the top of the ramp. So kat sini pun dia kosong, V equals to 0. So the kinetic energies at A and C are both 0. Okay, so we know that. Kita dah memang tentukan kat A ni kosong sebab kita start spring ni kosong KE dia. Kat sini pun KE akan jadi kosong. Note that the question asks for distance D along the ramp, not the height H. In part B, the system has both kinetic and gravitational potential at B. Okay. Okay, so what do we know about this one? What do we know? What else do we know? We know that our spring akan ada initial spring potential energy. KE initial adalah kosong. What else? Come on guys, what else? Cuba kita fikir logik. Apa yang ada lagi kat sini? Do we have KE final? We are supposed to have KE final because this guy is going to climb up the incline, right? So KE final is not equal to 0. What about my USF?
Zero.
My USF is equal to 0. So it is only going to be 0 if it is here. Okay, so kita solve kat sini dulu lah. Let's see. So kalau nak senang, kita akan try to solve our final state here. Okay, so at this point, when it reaches the equilibrium position, what is our USF value? When it reaches the equilibrium position? 0 kan? Sebab dia X kita adalah kosong. So kita cuba try to solve for that. Okay, and this V final refers to this point, EX equal to 0. Okay, so kita tahu 1 over 2, K is 6 to 5, XI is 10 centimeter, so that is 0.1 squared plus 0, 1 over 2, 6 to 5, kita tak payah kira sebab kosong. So that is equal to 0 sebab kita back to equilibrium. Bukan back lah, kita patah balik ke equilibrium. Betul lah, back to equilibrium. So this is 0, 1 over 2, M is 0.5, and V final is what we don't know. Tapi this is the V final at 0. So we have, let's just find out, we don't know. So 6 to 5 divided by 2 times with 0.1 squared, and then times 2. Answer times 2. Kenapa saya put negatif pula ni? 6 to 5 divided by 2 times 0.1 squared. Times 2 divided by 0.5, square root that. So I would know that my V final is 3.536. Kalau saya patah balik ke sini. Tapi tu dekat point 0. Saya tak nak tahu kat point 0 pun. Saya nak tahu dekat, kita nak tahu how far will the block go. So V final dah tahu kat sini. Kita akan travel kat sini. Lepas tu kita akan travel kat sini. Macam mana kita nak buat tu? And when it reaches C, it will become 0. So what should we do? So I have what if I want to make this into if I want to conserve the energy for this part so kita dah solve. This is not part A pun. This is just like preliminary results. So I want to solve for this system. So EI equals to EF. What do I have here? What is my starting point here? I have kinetic energy, right? I have kinetic energy. VI squared. This is my initial starting point. Do I have MGH here? Do I have MGH?
Not yet.
Not. So it's a 0, right? And for my EF, which is this point, they said that my KE should be a 0 because it comes to a rest. So my KE is 0 over here. Alamak, saya lupa nak tulis general equation dia. Let me rewrite that. So EI equals to, I am also just trying, saya pun tak tahu jawapan dia apa. So KE plus US equals to, sorry, this is UG. Kita dah tak ada, kita punya spring tu dah tak ada lah. So UG and then initial, KE final plus UG final. So they told us that our KE final should be 0 sebab at point C, where this is our final and this is our initial, at point C, our V is equal to 0. So we will use that. And we will know what is this, H. This is our final point. So this is going to be MGH. Ada tak dia beritahu? Kita tak tahu, kita nak cari D kan. So kita cari H dulu. So if we can find out what is H, can we find out what is T? If we can find out what is H, we can find out what is T, but we don't know the distance from here to here. Am I missing anything? Friction tak ada. V is initial plus 0 equals to 0 at the final point, and this is MGH. Tak ada lagi kan? That is it, right? Let's see the strategy again. In the absence of other forces, conservation of mechanical energy part applies to part A and B. In part A, the block starts at rest and is also instantaneously at rest at the top of the ramp. So kinetic energy are both 0. Note that the question asks for a distance D along the ramp. So,
Doktor,
yeah.
kalau dapat H, boleh ke guna Pythagoras
Kalau dapat H, boleh ke guna Pythagoras? So,
untuk cari D?
yes, tapi concern saya is that we would get D like this instead of here. Faham tak? This is H, right? So if patutnya boleh lah kan? Cuba je lah. Let's try. I think you're right. So kita akan guna Pythagoras after we get H. So H is theta diberi 30 degrees. If okay, let's just try it. Let's see if we get it right. So 1/2, M is 0.5. VI is, we got it just now, 3.536 equals to 0.5, 9.81 times H. So H would be, let's see if that is the answer. I also don't know, to be honest. 0.5 times 3.536 squared divided by 2 divided by 0.5 divided by 9.81. So our H is 0.637 meter. So using Pythagoras theorem, sine of 30 degrees, we get opposite over hypotenuse. Hypotenuse is our D. Opposite is H, 0.637 over D. So this guy divided by sine of 30 would give me a D of 1.27. 0.27. Okay, let's see. Takutnya. Oh, we got it. Yay. So it's approximately 1.27 or 1.28. So what do we do? What was the pening je soalan ni? Okay, so ada dua part kat sini. So EI equals to EF. First kita kena solve spring and what is the initial velocity at this point. Sorry, not the initial, the final velocity at equilibrium position. Mula kita compress. Bila kita compress, kita ada 1/2 kx squared. KE initial adalah kosong. When we release it and we go back to the equilibrium position, what happens is that all that 1/2 kx squared is now converted into KE. So kita tahu what is our V final here. This is the equation, 1/2 kx squared plus 0, KE 0. And then when we reach our equilibrium position where x is equal to 0, our US is also going to be 0. So all of this energy is now transformed into kinetic energy. Yay, so senang hidup kita. So kita dapat V final as this guy, units. And then I know what is the velocity here. I want to know how far does it go? How far does it go? So I know that V final has some value here. MGH is 0 here because this is our reference point. H equals to 0. And this is the H that we want to know. Okay. And they told us that this guy comes to a rest at point final. Dekat V, dekat point C ni dia cakap dia jadi kosong V. So we know that our KE should be 0 as well. Okay, so this is 1/2 MVI squared, some value. V final we got from here, plus 0, which is MGH, MG times 0 equals to KE final, which is 0, and MGH 0.5, 9.81. Kenapa saya tulis macam ni? That is so weird. So H kat sini ya. Okay, so you solve for H. So H dapat 0.637, and then using your Pythagoras theorem, sine of 30 will give you the D. Now, why did it work? And why didn't we get D for here? Because if we were trying to find the D for this guy, the angle would be different. But the angle over here is already given as 30 degrees. If we want to know what is the D from here to here, this would have a different theta. So this is how it works. The theta is 30. So it is specifically referring to this D only. You're referring to this D only. Okay, so that part confused me. I hope this is helpful because kita buat sama-sama. Is everyone okay? Faham ke what happened?
Faham.
Faham eh? Okay. So again, I'm going to repeat myself. So the tricky part here was not tricky. It was tricky for me lah. So if I find out H, shouldn't I get D from here to here? But the answer is no, because when I use this angle of 30 degrees, I am specifically referring to the D of over here. So it works. Pythagoras theorem holds. Memang betul lah sebab dia geometri je pun. Okay, so that is what happened. So let's see. We got 1.28, and then now next, how fast is the block going at half its maximum height? Dah susah soalan A tu, ada B pula. Aduh. Okay. So B, how fast is it going? So we want to know what is here. Now our KE is not 0. We have some mg. We know what is our H, so we can divide it by 2. So let's do it. Let's duplicate. Last one, lepas tu dah habis dah chapter 4. Yay. Saya pun tak sabar nak habiskan chapter 4. Saya padam. Betul. So we want to know what is the velocity at point B. Okay, so let's use this approach. But instead of E final at C, kita pakai E final at point B. So that's should be straightforward. Straightforward lah sangat. So EI equals to EF. EI sama macam tadi. 1/2 MVI squared plus with 0 because we started from this point. This is our initial and this is our final. Ni yang baru This is for part B. Kalau soalan boleh interrupt saya HD sin theta. Oh tadi Ikri pun dah jawab soalan. Thank you. Thank you Ikri, saya tak perasan awak punya chat. So 1/2 mvi squared plus 0 equals to, we want to know what is the final state over here. We have some mgh over 2 because we know that this is halfway of h, and then we know that we have some ke or 1/2 mv final squared at that point. Okay, so we have all m's here, boleh cancel out bagi hidup senang. We have vi, we have h, we don't know what is v final, so it should be easy. 1/2 vi, apa tadi vi kita, 3.536 squared equals to 9.81. Why is my 9 like that? Our D is, sorry, our H is 0.637. This is our H. Bahagi 2. 0.637 divided by 2 plus with 1/2 V final squared. So let's see if our answer is the same as the textbook. 3.536 squared divided by 2 minus with 9.81 times 0.0. Banyaknya nak ganti tekan kalkulator hari ni. Tolong kirakan sekali. Saya takut saya salah kira sebab banyak sangat. Square root. Saya dapat 2.5. Korang dapat 2.5 tak? 2.5. Okay. Thank you Daniel. Saya dapat 2.5. So for our V final. So dapat 2.5 meter per second. So from here, V initial kita adalah 3.536. Sampai kat sini 2.5. Sampai kat C kosong. So dia makin berkurang lah. So let's see. Yay. So we solved it. Okay, so that is it for today. Dah habis dah kelas kita for chapter 4. Next class we'll be talking about chapter 5. I will be assigning web assignment soon. I will let you know. Okay, so that is it. Ada soalan tak berkaitan spring ataupun anything related to chapter 4? Is everyone okay?
Okay. Boleh lagi.
Okay.
Yeah, so far so good. Okay, so kalau ada soalan, just ask me in the group or personally, okay? So take care everyone. Have a great rest of the day. Bye-bye.
Thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank
Thank you.
you, Doctor.
Thank you, Doctor.
Bye.
Doctor.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Bye. Welcome.